We keep hearing about the Big Bang and how the universe began with this tiny singularity containing all the matter in the universe. And then 13.8 billion years ago, it exploded. And ever since, it's been expanding. It's actually not quite right. The very first thing that happened in our universe was not the Big Bang, but rather the initial state of the universe, which is still unknown. We don't really understand what happened before the Big Bang, if there even was a before. So we have no idea what triggered the Big Bang. But what we do know is that the early universe had to be in a highly energetic state for the Big Bang to occur. And according to the most widely accepted model of cosmology today, the inflationary model of cosmology, the energy density of the universe was at least 10 to the 26th power joules per cubic meter. For comparison, that's about 10 million times the energy density of nuclear matter. That much energy should produce a tremendous amount of radiation, right? Should the night sky be filled with gamma rays and X-rays and other forms of high-energy photons? Well, it's not. The cosmic microwave background is basically devoid of high-energy photons. It turns out that there is a very simple explanation for this. Photons are quantum of light, or more accurately, they are quantum of the electromagnetic field. The electromagnetic field, like all fields in nature, has a particle associated with it, and that particle is the photon. But every field also has a wave associated with it, and the wave associated with the electromagnetic field is, of course, light. Every wave has a frequency, and the frequency determines the energy of the photon. The higher the frequency, the shorter the wavelength, and the higher the energy. Gamma rays and X-rays are high-frequency, high-energy photons. But the cosmic microwave background is mostly low-frequency, low-energy photons. This means that the high-energy photons must have been produced in the early universe, but they must have rapidly decreased in energy as the universe expanded. This is because as the universe expanded, the wavelengths of all the photons in the universe stretched. And when the wavelengths stretch, the frequencies drop and the energies drop accordingly. So here's the problem. If the early universe was so incredibly hot, shouldn't the night sky be filled with high-energy photons? Where are the gamma rays and X-rays? Turns out they're everywhere, but they're really hard to detect because they've been stretched to microwave wavelengths. They're all around us. In fact, the cosmic microwave background is filled with high-energy photons. It's just that those photons aren't gamma rays anymore. They're microwaves. They've been stretched by the expansion of the universe. Now, it is important to point out that this stretching of wavelengths is not unique to the cosmic microwave background. It's true of everything. All the light we see from distant galaxies has been stretched by the expansion of the universe. This is why the farther away a galaxy is, the more redshifted its light is. And it's this redshift that allows us to measure the rate of expansion of the universe. But the stretching of wavelengths due to the expansion of the universe is only thing that affects the wavelengths of photons in the universe. There's another process called Compton scattering, where photons scatter off of electrons, and each time a photon is scattered, there's a slight change in wavelength. The cumulative effect of all these scatterings over billions of years is a slight overall decrease in the average wavelength of the photons in the universe. This is known as the graying of the universe. So what we see in the night sky is the combined effect of two processes, the stretching due to the expansion of the universe and the graying due to Compton scattering. So, yes, The night sky is filled with high-energy photons, but they've even stretched in grade so much over the past 13.8 billion years that they no longer visible as gamma rays or X. They're only visible as microwaves. Now, some of you may be wondering if there is another process that may have affected the energy of the photons in the universe since the Big Bang. There is, and that's the inverse Compton scattering. This is the process where electrons are scattered off of photons and the electrons gain energy at the expense of the photons. This process tends to shift the photons to higher energies. However, the effect of inverse Compton scattering is much smaller than the effects of the other two processes I described earlier, the stretching due to the expansion of the universe and the graying due to Compton scattering. So, although inverse Compton scattering does shift some of the photons to higher energies, the effect is too small to explain the lack of gamma rays and X-rays in the night sky. So, there you have it. The reason the night sky is not filled with gamma rays and X-rays is because the photons that were once gamma rays and X-rays have been stretched and grayed so much over the past 13.8 billion years that they now microwaves. I hope you enjoyed this episode. If you did, please subscribe and watch the next episode.